Thank you, Win, for this invitation. I'm Dalei. Currently, I'm postdoc in PNL. I'm working with Gotham and Ruby. Um, Today, my topic is improving the soil radiation schemes in ELM land model. Focus on the impact of subgrade topography, snow grain shape, and light absorbing particles. First, I want to thank my co-authors for their contributions and help. Okay, I want to first briefly introduce the project I'm working on, Climate Process Team (CPT) project. Uh, this project title is 3D Land Energy Exchanges, Harnessing High-Resolution Terrestrial Information to Refine Atmosphere-to-Land Interaction in a System Model. The objective of this project is to advance the representation of radiation transfer processes in three assay models. Yeah, I'm working on the ESM. Specifically, this project plan to improve the radiation transfer model by accounting for the mountain topographic effects. Improve the black carbon and the dust effects on snow. Also, improve the multi-layer canopy transfer model by accounting for the black carbon and dust effects in the canopy. The first point is just to integrate the first three improvement with subgrid schemes in ELM. Okay, let's turn to today's presentation. Shortwave radiation schemes, also known as the shortwave radiation transfer. It describes the interaction between sunlight and the land surface, like this figure shows of the vegetation canopy radiation transfer process. The incoming radiation from the direct radiation, diffuse radiation goes through the canopy, and the canopy can absorb, reflect, and transmit the radiation. The transmitted radiation can be reflected or absorbed by the ground surface. Um, Based on this process modeling, we can know the light distribution. Like this figure shows the light distribution in a forest. We can know how much energy can be absorbed by the forest uh, or reflected by the forest. Generally, the land surface model just use the radiation transfer schemes to calculate the land surface albedo. Land surface albedo is very important parameters uh, uh, for the surface energy balance. This study will focus on the land surface albedo. Okay, this is outline. First, we focus on the topographic effects on land surface albedo. The second part is about the snow albedo. Uh, let's start from the topography. As you know, the topography has large effects on many land surface processes. One of the main reasons is that the topography can change the incoming radiation received by the land surface. Uh, this figure shows the sunny slope receive more radiation compared to the city slope. The vegetation type, the tree line, snow cover are very different between the sunny and the city slope. However, currently, CMIP6 model, most CMIP6 models just use plane parallel radiation transfer schemes for calculating surface albedo. This scheme just assumes the surface is flat. Don't account for the topographic effects. So this study will improve the radiation transfer model to account for topographic effects in ELM model. Then we will use the improved ELM model to evaluate the topographic effects at different spatial and temporal scales. We will use the remote sensing data to evaluate the performance of ELM. Okay, but how the topography can affect the solar radiation? This figure just show four aspects. First is the incoming radiation can change just because the slope, the inclined slope, incoming the direct radiation changed. and in mountains due to the obstruction by itself or other adjacent terrain. Yeah, uh, it can cause the self saddle and the cast saddle. Yeah, these regions cannot receive the direct radiation. The figure C just shows diffuse radiation can also decrease. This is because for flat surface, the diffuse radiation from the whole hemispherical sky, but here for the mountains, yeah, like this point, it just receive the energy from the part of the hemispherical sky. Yeah. Figure D just to show the adjacent terrain can reflect the radiation to the target uh, object. Yeah, so this part can increase the radiation uh, of the target. So finally, we include uh, well-validated subgrid topographic parameterization in ELM. This method just separates the total incoming radiation into 5 parts. Yeah, the first one is income direct radiation from sun. Two is diffuse radiation. Three is the direct radiation and reflected by the ground surface. Four is diffuse radiation reflected by the ground surface, and five is the remaining part, a coupled flux. Yeah, we use the Monte Carlo simulation to build the relationship between radiation components and some topographic factors. Yeah, the evaluation just shows this multiple linear regression have the good performance. Then we use the original PP scheme and the improved top scheme to test how the topography can affect the surface energy budget. This figure just shows the net solar radiation distribution for PP. That figure just shows uh, uh, relative difference between top and PP. We can say in the west region, there are difference yeah, positive, can be larger to 20%. This just means uh, in most of the Tibetan plateau region, top can increase net solar radiation, but in some north part of the Tibetan plateau, top can uh, also decrease net solar radiation. This figure just show how the topographic effects vary with elevation. Yeah, left figure is for net solar radiation. Right figure is so snow cover fraction. You can see with the increase of the elevation, there are difference. Yeah, top and the PP's difference increase. Yeah. Uh, Same conclusion for the snow cover fraction. Yeah, their difference uh, increase. Yeah, for snow cover fraction is negative bias and net solar radiation is positive bias. We further study how these topographic effects are sensitive to the spatial scale. This figure just shows the results for different spatial resolution. Yeah, 1/8 degree, uh, 1/4 degree, half degree, 1 degree, and 2 degree. For this uh, fine resolution, we can see many local spatial details. Yeah, but for this coarse resolution, 2 degree simulation, we can still see many different large difference between top and PP. Uh, Although some uh, negative and positive pairs cancel out each other in the north part. We further use remote sensing data, MODIS snow cover data to evaluate the model performance. Yeah, the left figure just shows the PP bias. Yeah, we can see ELM uh, overestimate the snow cover fraction in the western part. The right figure just shows the top bias minus PP bias. Yeah, we can see this value in the west region are negative. Yeah, that just means the top um, improve the model performance to some degree. Okay, let's turn to the second study, snow albedo. Snow play an important role in Earth's surface energy balance and water cycles. This is because the snow has the largest surface albedo in the Earth's surface compared to other land cover. Yeah, the fresh snow albedo can be larger larger than zero point 0.9. But for the ground surface, for the vegetation and soil, uh, their albedo are just from zero point 0.2 to zero point 0.3. The snow albedo can be affected by the snow green properties. Like this figure show, different snow greens just have different shape, different size. Yeah. Uh, uh, Another point is deposit black carbon and dust. Yeah, these light absorbing particles can darken the snow surface and decrease snow albedo. Yeah, the left figure just shows how the how the snow grain shape is determined. Yeah, it's related to the air temperature, water vapor saturation. Uh, the snow grain shape can also change with the snow age. Yeah, the right figure just show, yeah, black carbon or dust. Yeah, the labs can you have different ways to mix with snow. Yeah, left part is external mixing. Yeah, uh, white circle is snow and brown point is lab. Yeah. Red figure just show the internal mixing. Internal mixing just means yeah, black carbon or dust is inside the snow green. Yeah. However, uh, currently most land surface models just assume the snow is spherical and the labs are externally mixed with the snow. So in this study, we will improve the ELM model to account for different snow grain shape and also the internal mixing between lab and snow. And then we will use the improved model to analyze uh, how the snow grain shape and the mixing state can affect the surface energy and the water budget. We will also combine our first top study and this second snow albedo study to study how they can interact with each other. In order to answer this question, yeah, we first improve the snow albedo model, yeah, SNECA model in ELM, yeah, by accounting for four snow grain shape, yeah, sphere, spheroid, hexagonal, and the coach snowflake. We also explain the internal mixing and external mixing, yeah, inside the snow green and outside the snow green. Uh, After improving the snow albedo model, we first evaluate our ELM simulation with two remote sensing products. Yeah, this figure just shows the spatial pattern of snow cover fraction. Yeah, the first line is for winter, second line is for spring, and the first column is ELM, and this uh, multi-scats and spirits remote sensing data. We can say in winter, ELM spatial simulated spatial pattern are very similar as the model SAG and spirits, but in spring, ELM underestimates the snow cover fraction. This figure just shows the regional average, the mean value. For left figure is for the snow cover fraction, right figure is for the snow albedo reduction by lab, black carbon and dust. Yeah. And here the black circle is ELM and red and blue represent two remote sensing products. Yeah. We can say in winter ELM uh, uh, has good agreement with the remote sensing products. Yeah, both for the snow cover fraction and snow albedo reduction. But in spring, ELM underestimated the snow cover fraction, but overestimate snow albedo reduction. And then we analyze the surface radiation forcing induced by labs. Yeah. Uh, the first line is first row is winter, second row is spring, and the first column is uh, radiation forcing by all labs. Yeah. Central is black carbon distribution. Third column is dust distribution. Yeah, we can say generally spring, yeah, the surface radiation forcing is larger than winter. Yeah, and the radiation forcing uh, by labs in spring can be larger than 15. Oh, okay, yeah. We further analyze how the snow grain shape can affect the snow albedo and yeah, the snow albedo, snow cover fraction. Yeah, we calculate this non-spherical effect as the difference between non-spherical shape and the spherical shape. Yeah, we can say spheroid hexagonal plate and cold snowflake. Yeah, we can say cold snowflake has the largest difference from the sphere. Yeah, the snow albedo difference can be larger to zero point 0.1, and the snow cover fraction can be larger to zero point 0.2. Oh, this is results for how the mixing state can affect the snow albedo and the snow cover fraction. We calculate this mixing state effect as the difference between internal and external mixing. Yeah, we can say this value are negative. Yeah, that means internal mixing can um, can reduce uh, more snow albedo than the external mixing. Yeah, both the black carbon and dust mixing state can affect the snow albedo. So and then we analyze how the snow as far as how the snow shape can affect the surface energy balance. Yeah. Uh, this figure uh, this figure just show four important variables for the surface energy balance. Yeah. This is the surface albedo, this is net solar radiation, this is surface temperature, this is the latent heat flux. Yeah. We can focus on the surface temperature. Yeah. The x-axis is the snow cover fraction, y is the uh, difference caused by the snow grain shape. Yeah, we can say uh, for the temperature difference can be larger to 2K for the cold snowflake. Yeah, this difference are very large. Well, this is route for how the snow gray shape can affect the water cycle component area. Like this is snow melt, this is ET, this is run off. Yeah. Uh, so this is just to show the snow green shape has larger effects on the water cycle. Okay, and finally we can just combine our first top study and this snow albedo study to start how they can uh, interact with each other. Yeah. In this figure, figure B just shows the non-spherical effects for the cold snowflake, and figure C is the top effects. Figure D is figure C is top effect for sphere. D is top effect for coach. Yeah, we can see top effect generally is positive. Yeah, it can increase net solar radiation, but the non-spherical effects, yeah, generally are negative. Yeah, they can decrease net solar radiation. A just shows they are combined effects. Yeah, you can see some place are positive, some place are negative. Uh, so we can see uh, these three spherical, non-spherical shape effects, mixing state effects, and the local topographic effects. Their contribution can cancel each other. Okay, to summarize, yeah. First study just implement a subgrid topographic parameterization in ELM. Currently, this improvement has been merged in the main branch of E3SM. Based on this improvement, we found that topography can modify the surface energy and the snow processes. And the topographic effects are very sensitive to season, elevation, and spatial skills. and our improved top has better performance than PP when compared to modest data. And the second study just improved the snow radiation transfer model in ELM. Based on this improvement, we found that cold snowflake has the largest difference from the uh, spherical shape. And internal mixing can lead to larger snow albedo reduction and accelerate snow melt compared to external mixing of lap and snow. And finally, the combined effects of snow grain shape, mixing state, and the top, yeah, their combined effects can be positive or negative, depends on the specific conditions for a target pixel. However, currently these two studies just focus on the Tibetan Plateau, a hotspot region uh, uh, under climate change. Uh, in the future, we want to extend the experiment from the Tibetan Plateau to the global. And the second point is currently we just carry out the land-only simulation using ELM. In the future, we want to do the land atmosphere coupled run to analyze how the top, how the labs in snow can um, affect the atmospheric dynamics. And third point is, apart from the black carbon and the dust, these labs, the snow algae can also affect the snow albedo. Yeah, like this figure show, snow algae just change the snow color. Yeah, this is the red algae. So, how the snow algae can affect the snow and the surface fluxes. Yeah, we want to integrate yeah, uh, the snow algae spatial pattern in ELM and then use ELM to answer these questions. Okay, here just list some publications related to this work. Yeah, the first two papers uh, are related to the first study, top study. Yeah, first is published in GMD, another published in GEMS. And the second study, yeah, this paper, the third paper, uh, based on the third study, yeah, currently is under review in GMD. Uh, if you have, uh, if you want to get more details, you can check these papers. That's all from me. Thank you for your attention. If you have, I'm happy to answer any questions if you have.